Okay, so this is the class notes section for 4.3. There's not going to be a whole lot for you to write, but I would like you to listen to the video. There are a couple things to write, and then I want to go over some of these processes that we've learned in 4.3 that maybe aren't so clear just by reading them. So we know now that we have subatomic particles. J.J. Thomson discovered the electron, and he had that plum pudding model because he had to come up with something that had an electron in it. And then Rutherford comes along and he discovers that most of the mass of the atom is actually in the center in a nucleus. And after that, we discovered the protons and neutrons make up the nucleus. So when we're looking at subatomic particles, we have the three types: protons, neutrons, electrons. Protons and neutrons are in the nucleus. These are the only two that have significant mass. Both of these weighs approximately 1 AMU. And so the mass of an atom is made up of just these two pieces. They are all in the nucleus, and atomic number is used to determine the number of protons. So for our Plainsman periodic table, which if you don't have, you should get one from your teacher soon, is going to be this upper left-hand corner number. But no matter what periodic table you're looking at, there should always be a key that tells you where the atomic number is and the mass number, etc. Okay? So atomic number for protons. Neutrons are going to be the mass number minus the atomic number. And remember, the mass number of an atom is going to be a whole number because it's the number of protons plus the number of neutrons. The mass numbers on the periodic table aren't necessarily whole numbers, but we're going to talk about that in just a little bit. Okay, but mass number minus atomic number, you should always have a whole number of neutrons. So if you get a decimal, you need to round it to a whole number. And then electrons are going to balance our protons because the positive and negative charges of these two particles need to balance in order to have a neutral atom. Okay? So this is where we're starting, and then we're going to learn about something called shorthand notation. Now in shorthand notation, you have the symbol of your element, and then you have the mass number over the atomic number written on the left side here. Okay? And we're going to work with this to discover the number of protons and neutrons and electrons whenever we have an atom written in this shorthand notation. So I'm going to start by going through some of these sample problems with you. Okay, so right here we have number 16 says the atomic number of fluorine is 9. It wants to know how many protons and electrons are in fluorine. Well, the atomic number is the number of protons and the number of electrons. Okay, so when we have our neutral atom, okay, so atomic number for protons, atomic number for electrons. So you don't even need to use a periodic table for this question. It told you the answer right here in parentheses. So fluorine has 9 protons, 9 electrons, and etc. So whatever that atomic number is. Same thing over here. If they give you the atomic number, you automatically know the protons and the electrons. It's that, okay? 23 is going to fill into here. Now this one gave us the opposite. It gave us the number of electrons. Well, that is the number of protons, and that is the atomic number. And then we look over here at our periodic table, and the one that has the atomic number of 5 is boron. Okay? So that is number 16, number 17. Okay? All right, number 18, we get to our first question of shorthand notation. So here we have bromine, sulfur, silver, lead, and they gave us a specific mass for each of those. And you have to use the shorthand notation to discover how many neutrons are in the atom. Okay, now remember, neutrons are mass number minus the atomic number. Mass number minus the atomic number. So for part A, bromine, 80 minus 35, you get 45 neutrons. Sulfur, 32 minus 16, you get 16 neutrons, etc. Silver is going to have 61, and lead is going to have 125 with that mass of 207. Okay. 19 wanted us to express the composition of each atom in shorthand form. Now when you see an element name dash a number, this is mass number. So that number is going to be written in the upper left corner when we write out our shorthand notation. So for that carbon 12, carbon's symbol is C, the 12 comes up here, and then we need to write the atomic number down below. You can use a periodic table to find the atomic number, or you can use the data table 4.2, but the atomic number of carbon is 6. Okay? Boron 11 for part B, boron is B, 11 is our mass number, and then the atomic number for boron is 5. Beryllium 9, beryllium is Be, 9 is the mass number. Okay, and then you look at your periodic table and you see the atomic number is 4. And finally, oxygen 16, O16, has an atomic number of 8. So there's my shorthand notation for all of those elements. Okay, now we're going to talk about isotopes. Okay, isotopes are atoms of the same element. So if they're the same element, they have to have the same number of protons. Okay, protons define the element as that element. Okay, protons make you who you are. So same element means same number of protons. The difference for isotopes is the number of neutrons. They have a different number of neutrons in their nucleus, and therefore they're going to have different masses, and sometimes they're going to have different stabilities. Okay, some isotopes are totally stable, and some isotopes have a ratio of protons to neutrons that's unstable, and that makes them radioactive. Okay, they decay into other elements because they're not stable. All right, so that brings us to sample problem, well, I guess our class notes, okay, for isotopes, atoms of the same element, different numbers of neutrons, but different masses is kind of what we wanted you to write in your class notes. So atoms of the same element with different masses is what we wanted there. Okay, moving on to sample problem number 20 and 21. This is where we start talking about isotopes, okay? So number 20, you see that in there? Yep, okay. So 3 isotopes of oxygen are oxygen 16, oxygen 17, oxygen 18. Write the symbol for each, including the atomic number and the mass number. So that is the shorthand notation for each, okay? And then chromium isotopes are chromium 50, 52, 53. How many neutrons are in each isotope given that it has atomic number 24? So remember all these 50, 52, 53, those are masses, and they told us the atomic number. So to find neutrons, you do mass minus atomic number, okay? So we'll look at these oxygen isotopes here. So oxygen, let me just flip this over here, okay? Oxygen 16, oxygen 17, oxygen 18, all of them have the same atomic number or they would not be oxygen. So this one looks, this is your 3 shorthand notations, okay? Chromium 50, 52, 53. Chromium 50, 52, 53. And it told us that the atomic number of chromium is 24. So then you just subtract these 2 to get your neutrons. So we get 26, 28, and 29 neutrons, okay? So those are neutrons. Oops. By the way, if you haven't noticed, all of the sample problems are in the back of your book, including the work and the answers. So please, please, please don't ever leave a sample problem blank. That is not acceptable. Okay, moving on to interpreting data. Okay, we had this table here and it showed us the isotopes of several elements, and we're talking about these 2 questions. Which isotope of oxygen is the most abundant? Well, if you look at oxygen, it has 3 isotopes, and then there's the percent abundancies. This one's 99.759% of all oxygen. So oxygen 16 is the most abundant, okay? Part B, how could you use the atomic mass of helium to determine which isotope of helium is most abundant? Well, helium has 2 isotopes. One of them has a mass number of 3, the other one has a mass number of 4. If you look at the weighted average mass, the atomic mass of helium, this is what you would find in the periodic table if it went further than the 10th place. Okay, ours only goes to the 10th place, but this is the official atomic mass of helium. This is super, super close to 4 because helium-4 is almost all helium atoms. Okay, so 99.9999% of all helium weighs 4 AMUs, and so the average atomic mass is about 4 AMUs. So when you're looking at an atomic mass in the periodic table, if you round that to a whole number, it's going to most likely match up with the most common isotope for that element. Okay, now speaking of masses, isotopes are the reason why our mass numbers are not whole numbers in the periodic table. So take chromium, for example. Some chromium weighs 50, some weighs 52, some weighs 53. When you take into account how common each of those masses are, you take them, you create a weighted average mass, and for chromium it's 52.0. If we had a periodic table that went farther than that, then it would probably have a couple of outlying decimal places there, but 52 is the most common isotope of chromium because that averaged out to 52, okay? So speaking of weighted average mass, we put into your notes packet the steps for weighted average mass because in our experience teaching this class, These steps make a little bit more sense for people's brains than the ones in the book. Both problems work, you can work them out either way, but this seems to be a process that most students understand better. So when you're given percentages and masses of isotopes, we're going to assume we have 100 atoms in our sample, which means that we can multiply those percentages by the masses to figure out how much those atoms would weigh. We add all of our answers together to add up what all 100 atoms would weigh, and then we divide by 100. Okay? So I'm going to just do problem number